When we are designing large-scale distributed systems, we are often doing this for speeding up a complex task. But how does this work? Well, the baseline here is a sequential execution. Let's assume we have a set of tasks that all take the same amount of time to process. So on a sequential schedule, it takes as much time as we have tasks. Here, that would be 12 time units. Now, if we can execute the same tasks on 4 processing units in parallel, we can reduce the time to 3 time units. So our speedup would be the ratio between sequential execution and parallel execution. Here, a factor of 4. Amdahl's law of strong scaling describes this effect, but takes into account the portion of the execution that is not parallelizable. So in this case, the parallelizable portion of the code is P. And the execution of this part takes P over N, as we would assume. But then there is the non-parallelizable part, 1 minus P. And this still executes on a single processing unit and amounts to, well, 1 minus P. Now the overall speedup is much less than linear, and this is bad news. As you can see from the plot, the non-parallelizable part undermines the speedup. Even if your task is 90% parallel, as shown in the purple line, you will not get proportional speedup for more than 16 processing units. So here we can say it does not scale beyond 16 machines. Even worse, from about 512 machines on, there is close to no speedup at all. So we cannot accelerate this task infinitely by adding more machines. Once the parallelism is saturated, it will always run for the same duration no matter what we do. And this is part of the problem, because in distributed systems there are plenty of components that are not well parallelizable. Because, for instance, they form synchronization points between machines. Consistency protocols have this property, but effectively any blocking form of communication has. So does this mean we cannot build really large distributed systems? No, fortunately not. Because what Gustafson's law of weak scaling teaches us is that in practice we use larger resources for doing more work, and this is different from speeding up a fixed given task. Because if we just make the jobs larger, there is hope that the non-parallelizable portion stays roughly the same, and only the parallelizable portion increases. And in this case, we get linear speedup that we are looking for, where for every machine added, we get a corresponding return of investment because we get more work done. In practice, both laws are right, and the truth is in the middle. Parallelizing problems takes effort, and we have to be careful not to compromise our potential for speedup. Even when increasing the task size, we have to use non-parallelizable operations with care. When possible, we want to keep operations completely independent of each other, because then they are perfectly parallelizable and scale linearly. Calculating the GDP, for instance, for 2 different countries is independent when you keep the data separated. This is why large data-centric systems use partitioning or sharding when they can. When you are building a service for thousands or even millions of users, you need to limit the interaction between the users or resort to weaker forms of consistency that are inherently more asynchronous and thereby do not form strict synchronization points. This is how you make huge systems scale in practice.